Transients in capacitive network, the discharging phase. Now, if we consider this network, when the switch is connected to point A, the capacitor will start charging. Initially, as soon as the switch is closed, the current flowing through the circuit will be maximum. That is, IC will be equals to E by R. Then, as the voltage across the capacitor will increase, the value of IC will decrease. When VC will be equal to E, the current flowing through the circuit will be equal to 0. The voltage across the capacitor increases exponentially and the current flowing through the circuit decreases exponentially, as well as the voltage drop across the resistor R will also decrease exponentially. Now, this describes the charging phase of the capacitor. So, when the switch is moved from position A to position B, that is from point 1 to point 2, the network will look like this. Now, the capacitor will act as the source for this network. That is, the capacitor will be discharged through this resulting circuit. The voltage across the capacitor appears directly across the resistor to establish a discharge current. As soon as the switch is moved to position 2, the current will jump to a relatively high value. Then it begins to drop. It will start to decrease because charge is leaving the plates of the capacitor, which in turn will reduce the voltage across the capacitor and thereby the voltage across the resistor and the resulting current. One thing which you need to observe over here is, during the discharging phase, the direction of the current is opposite to that of the charging phase. That is, during the charging phase, the current will enter through the positive plate of the capacitor and leave through the negative plate. Whereas, during the discharging phase, current leaves the capacitor through the positive plate. The polarity across the resistor also changes, but the polarity of the capacitor will remain unchanged. Since the voltage across the capacitor is decreasing exponentially with time, hence the mathematical expression for Vc will be equal to E times e to the power minus t by tau. Tau will be equal to Rc. That is the capacitance of the capacitor and the resistor used in the discharging network. The current will decrease exponentially with time. Hence, the expression for the decreasing current will be equal to IC equals E by R e to the power minus t by tau. Since VR and Vc will become parallel in the discharging network, the equation for the voltage VR has the same format as Vc, which is VR equals E times e to the power minus t by tau. Here the uppercase letter E represents the supply voltage and E represents the exponential power. These figures basically shows the voltage across the capacitor, the current through the network and the voltage across the resistor during the charging and discharging phase. If we consider the first figure, which is this one, this basically shows the change in voltage across the capacitor during the charging and discharging phase. As I've mentioned earlier that it takes 5 tau time period for the capacitor to get fully charged, and it also takes 5 tau time period for the capacitor to be fully discharged. Hence, we will evaluate from 0 to 10 tau time period. So, when the switch is initially the switch is not connected to any point 1 or 2. As soon as the switch is connected to position 1, the voltage across the capacitor will start to increase, and it will increase exponentially. It takes 5 tau time period for the capacitor to have a voltage which is equal to the supply voltage E. Now, when the voltage across the capacitor is increasing exponentially, the current flowing through the circuit will decrease exponentially. When the switch is not connected to any position, the current through the circuit will be 0. As soon as the switch is connected to position 1, initially the current will rise very sharply and then it will start to decrease exponentially. Within a time of 5 tau, it will decrease from E by R to 0. When the current across the network will decrease, the voltage across the resistor, the potential drop across the resistor will also decrease based on Ohm's law, because V equals to IR. R is constant, therefore I is decreasing, hence the voltage across the resistor will also decrease. Now, when the switch is moved from position 1 to position 2, the network will look like this. Now the capacitor will be discharging and hence the voltage across the capacitor will decrease, and this will decrease exponentially. Since the polarity of the capacitor does not change between the charging and discharging phase, hence the graph is on the same side of the y-axis. When the voltage across the capacitor is decreasing, the current through the network will also decrease. But if you observe carefully, the direction of the current has been reversed. Initially during the charging phase, the current is moving in this direction. Now during the discharging phase, the current is moving in this direction. Hence over here during the discharging phase, the direction of the current has been reversed. For the resistor, the voltage across the resistor, it has also changed its polarity. That is, initially this was plus and this was minus. Now during the discharging phase, the polarity has been reversed. This becomes positive and this becomes negative. Similarly, the graph will also change its direction. Initially it was in this direction and now during the discharging phase it will be in this direction. In this example, we will assess both the charging and the discharging phase of the capacitor. The network used for the charging phase is the exact same network we have used in the previous example. So we are not going to recalculate the values of VR, IC and VC. We will be using the values we have calculated in the last example. Since the resistor and the capacitor are common to both the charging and the discharging network, hence tau for both charging and discharging phase will be same. That is, tau equals RC, which will be equal to 32 milliseconds. For the discharging phase, the switch is moved from position 1 to position 2, and this is how the network will look like. The direction of I has been reversed from what it has been in the charging phase, as well as the polarity of the voltage across the resistor. Hence, VC will be equal to e to the power minus t by tau for the discharging phase. That is, VC will be equals to 40 volts e to the power minus t by 32 milliseconds. IC will be equal to minus e by r. This minus sign indicates the fact that IC has been reversed in direction e to the power minus t by tau, which will be equal to minus 5 milliampere e to the power minus t by 32 milliseconds. And VR will be equal to VC, which is equals to 40 volts e to the power minus t by 32 milliseconds. A continuous plot for the charging and discharging phase appears as shown over here. The first graph basically shows the voltage of the capacitor against time, and the second graph shows the current that flows through the circuit with respect to time. For the capacitor to be fully charged, it takes 5 tau time period, and for the capacitor to be fully discharged, it takes another 5 tau time period. Therefore, a complete cycle of charging and discharging will take 10 tau time period. The current graph looks like this because during the discharging phase, the direction of the current is reversed. Hence, during the charging phase, the maximum current will be plus 5 ampere, and during the discharging phase, the current will also be 5 ampere, but it will have a negative sign which represents that the direction of the current has been reversed.